a 40-mile-an-hour gale, the feather span weaves like a ribbon in a swinging twist that you wouldn't believe possible unless you succeed.
Hey gang, you might have heard of the Reynolds number, but what the heck actually is it? It was not made by Ryan Reynolds, haha no. First coined in 1883 by a designer called Osborne Reynolds, it's what we call a dimensionless number. It can tell you a lot about a fluid flow, like whether it's smooth flowing, choppy, or somewhere in between. Depending on how big or small the number is, it can tell you if the fluid is laminar, turbulent, or transitional. Let's take a look at the equation. Rho is the density, V is the velocity, D is the diameter of a pipe, but can also be L, meaning characteristic linear dimension. And finally, mu is viscosity, dynamic viscosity, which is a measure of how well a fluid flows. A Hungarian fellow called Theodor von Kármán and a couple of other dudes studied how fluid flows always oscillate if an obstacle is placed in the flow like this. The phenomenon that happens is called a Kármán vortex street, which can do some wacky things like destroy bridges, destroy cooling towers, wobble plane wings, and lampposts, and also generate renewable electricity. But how do these two things relate? Well, there's a thing called the vortex shredding frequency, which tells us all about these Kármán vortex streets. The vortex shredding frequency is F in this equation, which uses something called the Struhel number, but we won't look at that today. The Struhel number is worked out with the Reynolds number, and what the heck? There we go! A direct relationship between the vortex thingies and the Reynolds number. Wow! With the stuff I'll be talking about today, it involves air, which has a density of 1.23 kilograms per meter cubed and a dynamic viscosity of around 3 times 10 to the minus 5 kilograms per meter second. But this does change with temperature and pressure, like if you're up in the atmosphere on a plane. When talking about air and the likes, this Kármán vortex street phenomenon is called aerostatic flutter. Let's take a look at that bridge. The Tacoma Narrows Bridge was built in the 30s and was opened to the public on July 1st, 1940. It was a big old bridge at 1.8 kilometers long. Sadly though, it collapsed just 4 months later on November 7th. The dang thing cost $6.4 million to make, which is the same as $115 million today. That's crazy! But why did it collapse? Most bridges are built like this, which allows air to flow freely through the bridge. But the Tacoma Narrow Bridge was built like this, forcing air to go over and under the bridge. Can you guess what happened? That's right! Aerostatic flutter. The Kármán vortex street downwind to the bridge got big enough and resonated with the bridge. Kinda like what happens when a wine glass breaks if someone sings it a song. The vortex shredding frequency matched the resonant frequency of the bridge, and the rest is history.
There it goes!
The same thing happened in Yorkshire back in 1965. Strong winds caused vortexes to form off some of the towers, which resonated with other towers and caused 3 of them to collapse. Looking back at the Reynolds equation, the only thing that's going to change much with air is the velocity and the diameter or length. In the cases of the cooling tower or the Tacoma Narrows Bridge, if the wind is going at the right speed for the right diameter or length, the Reynolds number will be the right number for the vortex shredding frequency to be the right number. That was a mouthful, hey! Very specific values will cause some things to wobble and maybe even break. You can design around this, however, so it doesn't happen again. With cooling towers, they can be bigger, smaller, further apart so that the vortexes don't affect them as much, or you can add these things called strakes, which break up the vortexes. With plane wings, you can't go above a certain speed, called a never exceed speed. Kinda catchy, hey? With bridges, they're not built solid, so the vortexes have a hard time forming. It's a good thing we know about this now, because when that bridge collapsed, there was one fatality. Tubby the Cocker Spaniel. Rest in peace, little brother.